Welcome back to Chapter 3 of Principles of Mathematical Analysis. So far we have defined convergent sequences and subsequences, and in both cases the definition refers to a limit. In this section, we meet a more intrinsic notion. A Cauchy sequence is one whose terms eventually crowd together among themselves, with no reference to any external limit point. From there, we will reach the central concept of a complete metric space, and close with a small but useful result on monotonic sequences in the real line. Here is the plan. After motivation, we give definition 3.8 of a Cauchy sequence and definition 3.9 of the diameter of a set, which together let us restate the Cauchy condition in geometric form. Theorem 3.10 records two facts about diameters that we will need next. The heart of the section is Theorem 3.11, the Cauchy criterion. In any compact metric space, and in particular in Euclidean space, a sequence converges if and only if it is Cauchy. From there, we name complete metric spaces in definition 3.12, and we close with the monotonic convergence theorem of definition 3.13 and theorem 3.14. Recall how we defined convergence in section 1. A sequence P sub n converges to P if its terms eventually crowd into every neighborhood of P. The catch is that the definition involves the limit P explicitly. To check that the sequence converges, we have to first guess what the limit is. In practice, we often want to know that a sequence converges before we have any idea what the limit looks like. Think of an algorithm that produces approximations one after another, or an infinite series whose partial sums we add up term by term. We would like a test for convergence that uses only the sequence itself, not a candidate limit. Cauchy's idea is exactly the right substitute. Instead of asking that the terms cluster around an external point, we ask only that they cluster around each other. The terms of a Cauchy sequence eventually become arbitrarily close to one another, and no fixed target point appears anywhere in the definition. The big payoff of the section is Theorem 3.11, which says that in any compact metric space, and in particular in R to the k, a sequence is Cauchy if, and only if, it converges. This equivalence is so useful that it earns a name, the Cauchy criterion. It will let us decide whether a sequence converges by inspecting the sequence alone. With this in mind, let us write down the formal definition. The formal definition mirrors the convergence definition with one crucial change. Convergence demands that P sub n be close to a single fixed limit point, P past some cutoff. The Cauchy condition demands that P sub n and P sub m be close to each other for any two large indices. So we now have two free indices and no fixed reference point. The intuitive picture is the same as before. Past some cutoff, all terms huddle inside a tiny window. The mathematical content is different in only one way, and it is exactly the way we wanted. The window is no longer pinned to any target. Here's the visual idea. The arrow is the real line, and the dots are the terms of a Cauchy sequence. The early terms, drawn in gray and labeled P sub 1, P sub 2, P sub 3, P sub 4, P sub 5, are scattered far apart. As we go further along, the blue dots start to cluster. From some index n onward, every term lies inside a tiny window, and the brace below the window indicates that its width is less than epsilon. The Cauchy condition asks that we can do this for any epsilon we like by choosing n large enough. Notice once again that that no target point is marked anywhere on the line. The dots are simply huddling together. To restate the Cauchy condition geometrically, we introduce the diameter of a set. Look at the set S of all distances between pairs of points of E and take its supremum. That number is the diameter, a single value capturing how spread out E is. Two subtleties are worth flagging. First, we use supremum, not maximum, because the largest distance might never be attained. Think of an open interval where points get arbitrarily close to the endpoints but never reach them. The diameter is the length of the interval, even though no 2 points realize it. Second, if E is unbounded, the set of distances has no upper bound, and the diameter is plus infinity. With this concept in hand, the Cauchy condition will become a statement about how spread out the tails of the sequence are. Combining the last two definitions gives a clean reformulation. For each n, form the tail E sub n by collecting P sub n and everything that comes after. The sequence is Cauchy, precisely when the diameters of these tails shrink to 0. This is the same Cauchy condition recast. The tail has diameter less than epsilon if and only if any two of its members are within epsilon of each other. The reformulation is more than cosmetic. In the proofs that follow, we want to treat tails as geometric objects, and diameter is the right measurement of how concentrated they have become. The Cauchy condition is, in effect, a shrinking tails condition. Theorem 310 records two geometric facts we will need for the Cauchy criterion. Part A is the simpler one. The closure of a set has the same diameter as the set itself. Why should you expect this? Closing up adds in the limit points, and every newly added point sits arbitrarily close to a point that was already in E. So any pair of points in the closure can be approximated by a pair already in E, with their distance approximated too. Approximated, not increased. So the supremum of distances cannot grow. The precise argument follows in a moment. Part B is the geometric heart of the section. It says, take a nested decreasing sequence of non-empty compact sets whose diameters shrink to 0. Then their intersection is a single point. Two hypotheses each play a role. Non-emptiness, together with compactness, guarantees that the intersection is non-empty. By Theorem 236 from Chapter 2, without non-emptiness, the intersection could already be empty after the very first set. The diameters shrinking to 0 forces the intersection to contain at most 1 point. Together, exactly 1 point. This is the engine that will drive the proof of the Cauchy criterion in compact spaces. Here is the picture behind Part B. The nested sets are drawn as decreasing red disks, labeled K sub 1 on the outside, down to K sub 4 on the inside, with the shading getting darker as we go in. Each set is non-empty, compact, and contained in the one before. The diameters are also shrinking. In the limit, they go to 0. The orange dot in the middle is the unique point lying in every set, and that is the only point of the intersection. The picture is the only possible behavior. A single point is squeezed out at the end. The proof has two halves. The easy direction is just monotonicity of the supremum. E is contained in its closure, so every distance between 2 points of E is also a distance between 2 points of the closure. Taking suprema, the diameter of E is at most the diameter of the closure. The other direction is the substantive half. Pick any 2 points P and Q of the closure. By the definition of closure, Each is approximated within epsilon by a point of E. Call them P prime and Q prime. The triangle inequality, displayed on the slide, routes the distance from P to Q through P prime and Q prime, paying twice epsilon of slack and otherwise charging only a distance inside E. Since epsilon was arbitrary, the diameter of the closure is at most the diameter of E, and we have equality. The proof splits into two steps. Step 1 produces at least one point of the intersection. Here is where both hypotheses on the K sub E n pull their weight. Each K sub n is non-empty and compact, and they are nested. Any finite subfamily intersects in its smallest member, which is non-empty by hypothesis. So the family has the finite intersection property, and theorem 2.36 from chapter 2 then gives that the full infinite intersection K is non-empty. Step 2 rules out two or more points. Suppose, for contradiction, that K had two distinct points. Then the diameter of K would be strictly positive. But K sits inside every K sub n, so the diameter of K sub n is at least the diameter of K for every n. That contradicts the assumption that the diameters of K sub n tend to 0, so K has exactly one point. Theorem 311 has three parts. Part A is the easy direction and holds in any metric space, with no extra assumptions. Every convergent sequence is automatically Cauchy. The reason is intuitive. If the late terms are crowding inside an epsilon ball around the limit P, any two of them are within twice epsilon of each other by the triangle inequality. So crowding around a single point automatically forces crowding around each other. Convergence implies Cauchy, with no special structure on the space at all. Part B is the deep direction, the converse of Part A. It needs an extra hypothesis. The ambient metric space X must be compact. Under that hypothesis, every Cauchy sequence converges to a point of X. The compactness assumption is essential. We will soon see that in the rationals, the decimal truncations of the square root of 2 form a Cauchy sequence that has nowhere to converge, because the would-be limit is irrational and lies outside the space. Compactness is the structural assumption that closes off this kind of escape. Part C specializes to Euclidean space R to the K. Every Cauchy sequence in R to the K converges, no compactness assumption needed on the ambient space. This is the Cauchy criterion in its most familiar form. The proof of Part C is a quick reduction to Part B. A Cauchy sequence is bounded, and bounded subsets of R to the K sit inside compact sets, so Part B applies. We will write this all out below. Pause to take in the punchline. Convergence, as we defined it, refers to a limit, but the Cauchy condition refers only to the sequence. In R to the K, the two are equivalent, so we can decide convergence without ever producing the limit. This pair of equivalent statements has its own name, the Cauchy criterion for convergence. With the criterion stated, we now turn to the proof. The proof of Part A is a one-line application of the triangle inequality. Pick n so that every term past index n is within epsilon of the limit P. The displayed inequality then routes any two such terms through P, paying epsilon on each leg for less than twice epsilon total. The arbitrary epsilon and the resulting twice epsilon both shrink to 0, so the Cauchy condition holds. Notice we have not used anything special about the ambient space. This argument works in every metric space. which is exactly why Part A holds without any extra hypothesis. The proof of Part B deserves a roadmap. The challenge is to produce a limit P without ever being told what P is. The strategy is to corner P geometrically. The closure of each tail forms a region the sequence can never escape. Compactness makes those regions compact, and the Cauchy condition makes them shrink. Theorem 3-10, Part B, then squeezes out a single point common to every region, and that point must be the limit. The 5 bullets on the slide implement this plan using only tools we already developed in Chapter 2 and earlier in this section. Step 1 turns the Cauchy condition into a geometric statement. For each n, the tail E sub n collects every term from index n onward. We saw a few slides ago that being Cauchy means the diameters of these tails shrink to 0. We now want closures, not the tails themselves, because closures are closed, and we will need closedness in the next step. Theorem 3-10 Part A tells us that closure does not change diameter, so the closures shrink to 0 too. The conclusion, marked as equation 3 on the slide, is the geometric form of the Cauchy hypothesis we will use through the rest of the proof. Step 2. Line up the hypotheses for theorem 3-10 Part B. Each closure E sub n bar contains the term P sub n, so it is non-empty. It is closed in the compact space X, so by theorem 2.35 from Chapter 2, it is also compact. The closures are nested because the tails themselves are. Combined with equation 3 from Step 1, which gave the diameters tending to 0, every hypothesis of theorem 3.10 Part B is satisfied, and we conclude there is a unique point P lying in every closure. This P is our candidate limit. Step 3 closes the loop and shows that P really is the limit. Fix any positive epsilon. Equation 3 from Step 1 lets us pick a cutoff n sub 0 past, which the tail closures all have diameter less than epsilon. Here's the punchline. P sits inside that tiny closure, and so does every term P sub n for n past the cutoff. 2 points sharing a set of diameter less than epsilon must be within epsilon of each other. So P sub n is within epsilon of P. That is convergence, and Part B is done. The whole argument was an application of the nested compact squeezing principle from Theorem 3.10. Part C is now a quick consequence of Part B. Take a Cauchy sequence in R to the K. Because it is Cauchy, some tail has diameter less than 1, and the whole range of the sequence is the union of that bounded tail with finitely many earlier terms, which is itself bounded. By Theorem 241 from Chapter 2, every bounded subset of R to the K has compact closure, so the sequence lives inside a compact subset of R to the K. Part B applies inside that compact set and gives convergence. With Theorem 311 in hand, we can name the property. A metric space is complete if every Cauchy sequence in it converges to a point of the space. Theorem 311 then reads cleanly: every compact metric space is complete, and every Euclidean space is complete. The word complete is well chosen. A Cauchy sequence is a sequence that is trying to converge somewhere. If the would-be limit is missing from the space has a hole that the sequence falls through. Completeness says there are no such holes. Every limit a sequence wants is actually present. The deeper reason the real line is the right setting for analysis comes down to this single property. Theorem 311 also has an important corollary. Every closed subset of a complete metric space is itself complete. The argument is short. A Cauchy sequence in E is in particular Cauchy in the larger space X, which is complete, so the sequence converges to some point P in X. Now E is closed, so it contains all its limit points, and P must lie in E. Thus every Cauchy sequence in E converges in E, which is the completeness of E. Here is a textbook example of a metric space that is not complete. Take the rational numbers with the usual distance, absolute value of the difference, the decimal truncations of the square root of 2, namely 1.4, 1.41, 1.414, 1.142, and so on, are all rational, and they form a Cauchy sequence because any two of them agree up to a power of 1/10. But in the real line they converge to the square root of 2, which is not rational. So this Cauchy sequence in the rationals has no limit inside the rationals. The rationals fail to be complete. The real line was specifically constructed to fix this. Before the next definition, contrast convergence with boundedness. We already know that in R to the k, every convergent sequence is bounded. This is Theorem 3.2 Part C from Section 1. The converse fails in general. The alternating sequence -1 to the n is bounded but does not converge. There is, however, one important case in which convergence and boundedness coincide, namely monotonic sequences on the real line. That is the content of Theorem 3.14, which we are about to state. Definition 3.13 just names what we already had in mind. A sequence climbs if each term is at most the next, and falls if each term is at least the next. The inequalities are non-strict, so the sequence is allowed to stay put for a step or two without disqualifying itself. Constant sequences count as both increasing and decreasing. Why isolate this class? Because monotonic sequences are well behaved enough that, as we will see in Theorem 3.14, the question of convergence reduces to the much simpler question of boundedness. Here is the theorem itself. If a sequence of real numbers is monotonic, then convergence and boundedness are equivalent. The forward direction that a convergent sequence is bounded is Theorem 3.2 Part C again, and holds with no monotonicity assumption. The reverse direction is the content. We will see that the supremum of the range of an increasing bounded sequence is in fact its limit. The least upper bound property of the real line, established in Chapter 1, is exactly the tool we need. Here is the picture behind the proof. The arrow is the real line. The blue dots labeled S sub 1, S sub 2, S sub 3, and so on march steadily to the right because the sequence is increasing. The orange tick marks the supremum of the range of the sequence, which we are calling S. The brace at the top marks an epsilon window just to the left of S. Once any term enters that window, every subsequent term must also be in the window. It cannot fall back, because the sequence is increasing, and it cannot exceed S, because S is an upper bound. So from some index n onward, every term lies between S minus epsilon and S, which means the sequence converges to S. We prove the increasing case. The decreasing case is the same argument with infimum in place of supremum. Assume the sequence is increasing and bounded. Let E be the set of terms. Because E is a non-empty bounded subset of the real line, the least upper bound property guarantees a supremum, which we call S. Every term of the sequence is at most S by the definition of supremum. Now the main argument. Fix any positive epsilon. The number S minus epsilon is strictly less than S, so it cannot be an upper bound of E. Some term S sub n exceeds it. Because the sequence is increasing, once we pass index n, we stay above S sub n, and we never climb past the upper bound S. So for every n, at least n, the term S sub n lies in the half-open interval from S minus epsilon up to S. That is exactly convergence to S. Let us recap. The first key takeaway is the new definition. A sequence is Cauchy if, for every positive epsilon, there is a cutoff index past which any two terms are within epsilon of each other. Crucially, the definition makes no reference to a target limit. It only uses distances between terms of the sequence. The second takeaway is Theorem 311, the Cauchy criterion. In any compact metric space, and in particular in R to the k, being Cauchy is equivalent to being convergent. This lets us decide convergence without producing a limit, which is one of the most useful tricks in analysis. The third takeaway is definition 3.12. A metric space is complete if every Cauchy sequence in it converges. Theorem 3.11 says that compact metric spaces and Euclidean spaces are complete. The rationals are not complete. They have Cauchy sequences that try to converge to irrational numbers. Completeness is the absence of holes, and it is the central structural property that makes the real line so useful for analysis. The fourth takeaway is Theorem 3.14, our small but very useful result for monotonic sequences. A monotonic sequence on the real line converges if and only if it is bounded, and the limit is either the supremum in the increasing case or the infimum in the decreasing case. Coming up next is Section 4 on upper and lower limits, where we extend the idea of a limit to two related quantities, the limit superior and the limit inferior, which always exist for any real sequence and capture the two extreme cluster points. Thank you for following along, and see you in the next section.